All right, thank you, and thanks for sticking around. A little bit about me. I did my PhD with Sergei Tvachnikov, finished in 2017. I spent a couple years at Lehigh University with Don Davis, a semester at MSRI, and 2 years at Carnegie Mellon. And if you happen to know the named people, you will know that they all do very different things. Sergei is in dynamics and geometry. Don is an algebraic topologist, and Florian does some topological combinatorics. So I've had some wide range of problems I've worked on, and today I'm just going to give a sample of a couple of those. So let me start with a very simple question. Does there exist a loop in R3 without any parallel tangent lines? So in the plane, this is, of course, not true. A circle in the plane will have many parallel tangents. But if you don't ask the question for a circle, but rather R, you can do this. You can have a parabola, which has no pairs of parallel tangent lines. This is possible, and here's an example. And we can generalize this and ask, if you give me a smooth manifold, what's the minimum dimension we can put it in so that it doesn't have parallel tangent lines? So this is not, I'm not asking for no two parallel tangent spaces, but actually no parallel tangent lines. So every pair of tangent spaces should span 2 n dimensions if n is the dimension of the manifold. So some simple examples. For R, it's 2, the parabola. For R2, you can look at the complex map, Z maps to Z, Z squared, and that would be totally non-parallel. And S1, we saw the example you can put in R3, but for other simple spaces, I have no idea what this number is. So maybe very briefly, I want to mention that this is related to some sort of famous classical algebraic topology questions. So if you don't know what this is referring to, that's okay. But we can use it to get these bounds, at least. And you can see that we know it for 1 and 2 and nothing else. And one noteworthy thing is that the only possible dimensions where you could put Rn and R2n with this property are 1, 2, 4, and 8. So that's known for 1 and 2, but not 4 and 8. Okay, so let me talk about a simple construction. If you take any map into Euclidean space, we can form this map on the product where you add the 2 images together. And it's not important to think about this geometrically, but we should observe that if F is totally non-parallel, then what that says is that for distinct X and Y, their tangent spaces span 2 n dimensions. So this says that G is an immersion on the configuration space. And in fact, this G is Z2 equivariant, so it's an immersion of the unordered configuration space. And as soon as you do this, it's possible to compute obstructions because you have this bundle monomorphism of the tangent space of the unordered configuration space, and you can compute things like Stiefel-Whitney classes to get some obstructions. So I spoke with Don Davis about this, and he was able to compute these obstructions in the case of projective spaces of powers of 2, which sort of classically are the worst things to embed and immerse. They take the most dimensions. And he showed that they do not immerse, that this unordered configuration space does not immerse in 4 times its dimension minus 2. So we get this very strong bound on the totally non-parallel dimension. And I say this is very strong because any n manifold, a generic map into 4 times its dimension is totally non-parallel. So he narrowed this down to 1, and then I was able to show that every smooth n manifold admits a totally non-parallel immersion into, in fact, this dimension. So this uses the H principle technique called removal of singularities due to Elyashberg and Gromov. And you can sort of think of it like a Whitney type theorem. Whitney says that for immersions and embeddings, they exist in 1 dimension lower than is given by genericity. So this is sort of in that sense, Whitney type theorem. And I want to mention that this is a pretty weak result. I mean, it's totally expected in this, thinking about it in Whitney terms. So some open problems are to study an H principle for totally non-parallel immersions. Or, I mean, there are many other configuration space conditions which have been studied recently. And basically the game is as follows. You have some condition which is on a configuration space. So it involves k tuples of points and their derivatives, some sort of non-degeneracy condition. You build some algebraic thing out of it, whether it's on the configuration space or a bundle over it, and then you can compute obstructions by algebraic topology. And this has been done very much, but there's been almost no study of existence of these types of things. So for some of these configuration space conditions, there are k regular embeddings, R neighborly embeddings, totally skew is totally non-parallel. This is the first existence result for any closed manifold except for the circle.
I have a question.
Yep.
When M is spent in, as you mentioned, the non-ordered configuration space will be singular. So what do you mean by immersion?
Sorry, I didn't understand.
This unordered configuration space will be
Yes.
singular. So what do you mean by immersion?
So by the configuration space, I mean the product minus the diagonal and
Minus the diagonal.
minus the diagonal,
sorry.
yeah.
Now it's hard. Okay, so
Yeah. Okay, so there are some sort of open things to think about. Something completely different I want to talk about. So if you have a space with a free Z2 action, you can define what's called the co-index. And this co-index is the dimension of the largest sphere, which maps Z2 equivariantly into it. So it maps so that it commutes with the antipodal map. Borsuk-Ulam tells us that the co-index of Sn is n, because it says that there's no Z2 equivariant map from Sn plus 1 into Sn. And what we're interested in is studying this Z2 co-index of the space of embeddings of some space into Rd. So you can put several different interesting Z2 actions on this. One is you take an embedding and you reflect it in a hyperplane. And another one is you take an embedding and you take its antipode, so you reflect in that sense. And so maybe given a space, you can think about this co-index as some sort of measure of the equivariant topology of the space, sort of how rich is this space of embeddings in that sense. So we can quickly observe that the co-index being 0 is related to whether or not X embeds into Rd. And if you think about what it means for the co-index to be 1, this would mean that there's a loop in the space of embeddings, which is commuting with this antipodal map. So if you look at two antipodal points, one should go to its mirror image. So this is related to the question of chirality. A, say, subspace of Euclidean space is chiral if it cannot be deformed to its mirror image. So sort of knowing something about the co-index would be related to questions of chirality. So for the next statement, I want to fix the action on the embedding space to be the one where we take an embedding and negate everything. And I want to convince you that if we look at the space of embeddings of the projective plane into R4, then that has co-index 3. And the idea of what I will say is to show these bounds. So the lower bound is actually very simple. I have to exhibit a map from S3 into the space of embeddings, which commutes with the antipodal map. So take an embedding of the projective plane into R4 and hit it with all the unit quaternions, and that's it. When you increase the target dimension, the co-index should not decrease, because we could put R4 and R7, put the embedding there, and if the sphere hits that embedding space, then it works in higher dimension. So the first two inequalities should be fine. And for the last one, I want to use this result. So this result, we have a simplicial complex on n vertices. And we have a couple parameters here, which I'm going to talk about in a second by example, instead of maybe thinking about it, and some number theoretic condition on these parameters. And if this number theoretic condition is satisfied, we get an upper bound on co-index. So I want to, instead of thinking too hard about this, just do it by example. So this is a triangulation of RP2. You should understand this, that opposite points are glued to each other. So this triangulation is a simplicial complex. All of the edges are there. It has a complete one skeleton. And these are the two-dimensional faces that are in there. And I want to tell you how to build what's called this Kneser graph of a simplicial complex. So we'll do it by example. To build this Kneser graph, we're going to make the vertices the minimal non-faces of this complex. So in this case, I've listed all the two-dimensional faces which are not present there. And then we'll connect two vertices if they're disjoint. And in this case, you can stare at these and see that none are disjoint. So this graph that we created, this Kneser graph, will just have 10 vertices and no edges. And the chromatic number of that is 1. So now we did this for this triangulation of RP2. So let's look back at this statement. We had a simplicial complex on 6 vertices. And we found that the chromatic number of its Kneser graph was 1. So in case we choose D equals 7, then M is 7 minus 6 plus 1 plus 2 is 4. E minus M is 3. 3 and 4, if you look at their binary expansions, don't have a 1 in any slot shared. So we get that the co-index is less than or equal to 3.
Doesn't it depend on how you triangulate it?
Well, you'd want to choose the best one. Another interesting result you could get from this, if you choose D equals 3, then M equals 0, and this also satisfies the hypotheses, and you get this non-embeddability result of RP2 and R3. So this sort of technique where you can learn something about the topology or embedding in terms of these combinatorics of triangulations was new to me. And we pushed this as far as we could and obtained results for other spaces. And we defined this notion of coupled embeddings, which seems to be a pretty good generalization of embeddings, but for products of manifolds, and develop some similar theory there.
Can you say something about why the binary expansion?
Yeah.
Relevance?
Yeah. So yeah, so there's this, I guess I would call it generalization of Borsuk-Ulam, but you can look at maps like this and ask that they be antipodal in both factors. So, I mean, the way I would state Borsuk-Ulam is sort of an antipodal map from here to here must hit 0. If we think of Borsuk-Ulam that way, then we could also look at a similar thing where it's Z2 equivariant in both slots. And if it is, then this would descend to a map of RPN cross RPM to RPN plus M minus 1. You look at the map in cohomology and you look at the product formula, and what pops out when you write out this product formula is a bunch of binomial coefficients. And when you see that they have to be 0, it comes down to this condition. So this was first studied by Hopf, actually. It was one of the first applications of cohomology theory. Yeah, so that's a really neat thing that the binary expansion sort of pops out of this. Yeah, very briefly, this is more just to see some keywords of other things that I've worked on in case you want to chat about them. Fibrations of R3 by oriented lines. You can generate one of these by taking a vertical line, surrounding it by family of nested hyperboloids. They're all ruled, so you can consider the rulings. And these are related to great circle fibrations, tight contact structures on R3, and non-singular bilinear maps. This middle picture is looking at the geodesic complexity of the configuration space of the Y graph. You have several points that you want to get to each other on the Y graph without colliding. And I studied some various billiard problems on Finsler manifolds and some outer billiard systems. So happy to talk about any of these if you're interested. Thank you.